Good morning friends, we will be continuing with driving point impedance function or emittance function. We have seen the properties to be satisfied are poles and zeros of the emittance function must lie in the left half plane, left half of S plane. Then poles and zeros on the imaginary axis must be simple. On the imaginary axis must be simple. These are two very important properties. And then to ensure that poles and zeros lie in the left half of S plane, actually all the coefficients of the polynomials, all the coefficients of numerator and denominator polynomials, we were using PS and QS, okay, PS and QS must be positive. All the coefficients of PS and QS must be positive, okay, and real. Then the difference in the degree, of PS and QS, the degrees of PS and QS must be restricted to 1. All right, difference in the degrees must be restricted to 1. And as a corollary to this, that means I will not write as an extra point, it is to ensure this, Routh-Hurwitz criteria must be satisfied. The criteria all of you know, we discussed last time. Anyway, we will work out one or two simple problems later on in the tutorial. And lastly, what was our last point we discussed? A real part of Z or Y for all positive values of omega must be greater than 0 for all real omega. Okay. We will see where are the exceptions coming. Where do you think some of these conditions may not be strictly satisfied? Poles and zeros must lie in the left half plane. All right. On the imaginary axis, this must be simple. All the coefficients of PS and QS must be positive and real. Is it necessary that all of them should be positive? There can be a situation when alternate terms are present. That is, you have an even polynomial or an odd polynomial. This situation can come when you are having, say, purely inductance capacitance circuits, LC circuits, where there is no dissipative element. When there is no dissipation, then there can be a sustained oscillation. For example, I can have a function S by S squared plus 9. Suppose Zs is this. So in the numerator polynomial, you are having S, the real term may or may not be present, the s to the power 0 term. Here s to the power 1 term is missing. Will it be a positive real function? Yes, it will be. This is the only exception. That is, if alternate terms are present, this is an even polynomial, this is an odd polynomial. So this you can see, this is nothing but an LC parallel combination. We will see how to realize this very soon. Okay. Now, if the numerator or denominator, that is PS or QS, contains only even or odd terms, it may be possible to have a realizable impedance function. Okay. Other conditions are to be satisfied. All right. Now let us see one or two simple functions we will take, and then we will see the properties of LC networks. We will take the typical structures of two element networks, that is either LC or RC or RL. Okay. So what would be the impedance or admittance function like for such networks consisting of only two types of elements, that is L and C or R and C or R and L? What will be the network function like? Let us take LC combination. Let us have a simple series circuit, L and C. So what will be ZS? LS plus 1 by CS. If you simplify this, LC S squared plus 1 divided by CS. Okay. Let us take the admittance corresponding to this YS, corresponding to this will be CS by LC S squared plus 1. Where are the poles and zeros located? For the impedance function, there is a pole at the origin, all right, and there are two zeros where? 1 by root LC and plus minus 1 by root LC? J. So here and here, this is S plane. So roots are all imaginary. Okay, this is 1 by root LC, this is imaginary, this is minus 1 by root LC. Okay, if you consider this is Z, if you consider Y, the admittance function, where are the poles and zeros located? It will be a 0 now. Wherever you had the 0 earlier for Z will become poles. Let us take another example, L and C in parallel. What will be Z? LS into 1 by CS divided by LS plus 1 by CS. Okay, if I multiply throughout by CS, it becomes LS by LC S squared plus 1. So for this LC parallel combination, this is for series. For the parallel combination, what will be ZS? The 0 at the origin, pole at 1 by root LC. on the imaginary axis. Okay, this is Z, and what will be the corresponding Y? What will be the corresponding Y? It will be just reverse. So this will be a pole, this will be zeros. Okay. Now, can you draw any conclusion from this?
Once we know one plot, then we can get
The structures of poles and zeros. Poles and zeros are all on the imaginary axis, number one. Number two, poles and zeros are coming alternately. We will have a little higher order functions and then see. And then the origin is always either a pole or a zero. Is there any pole or zero at infinity? If I put s equal to infinity in the first case, if I put s equal to infinity, Zs will tend to infinity. This is a higher order, s square by s, so it will be LCS, and s tending to infinity, so Zs will be infinity, and when a function blows up to a very high value tending to infinity, it is a pole, corresponding s will be a pole. So we will show a break, and this is at infinity, it is a pole. Here also at infinity there is a pole. Similarly here at infinity Ys becomes 0, so at infinity this will be a 0, at infinity this will be a 0. Similarly here you can see for Zs this will be a 0, okay. Similarly this one will be a pole at infinity. Let us take another example. Say this is 1 Henry, 1 farad, 1 Henry, 1 farad. What will be Zs like? Ls plus 1 by Cs plus Ls into 1 by Cs by Ls plus 1 by Cs, and L is equal to 1, C is equal to 1. So this will become S plus 1 by S plus S by S squared plus 1. Is that all right? So that gives me S by S squared plus 1. This is S squared. What will be the numerator like? S squared plus 1 whole squared plus S squared. So s to the power 4 plus 3s squared plus 1. Okay. Simplify this, s squared plus 1 whole squared plus s squared. So it's 4 plus 3s squared plus 1. Okay. There are two real roots. What are the roots? S to the power 4. Okay. S to the power 4 plus 3s squared plus 1. I can write s square as x, so it is basically a quadratic in x. So what are the roots of x? Minus 3 plus minus root over 9 minus 4 by 2. So minus 3 root 5, so 2.24 divided by 2. Alright. So 3 minus 2.24, so 0.76 by 2.38 approximately, and this is 5.24 divided by 2. Is that all right? 5.24 divided by 2, so 2.62. S squared plus 2.62 divided by S into S squared plus 1. So let us sketch the poles and zeros for this. Origin is a pole, it is in the denominator. 1 is a pole. Then root over of 0.38, approximately 0.62, 0.63, so that is a 0, and root over of 2.62, that is 1.63 or so, 1.64 approximately, and this is a 0.62. You have got zeros, and then at infinity, I am not showing the negative values of omega, it is identical. Okay. At infinity, this is infinity, so this is a pole. So you see, pole 0, pole 0, pole, again they are coming alternately. Okay. So LC network, if we have similar to this, if I take YS, an admittance function, the poles and zeros will be just replacing, interchanging their positions. This will be a 0, this will be a pole, and so on. So there also pole 0, poles and zeros will be appearing alternately. Henceforth, we will draw a diagram . So this is omega, because now we can take the frequency as the axis and corresponding value of x omega, x omega. How will x omega vary with omega? Let us go back to the first problem. Suppose we have just an inductance. What will be its x, j, omega, L? So if I write this as jxl, jxl, then xl will be varying linearly with frequency. Is that all right? With a slope of L, with a slope of L. So this is XL. What about XC? If I have a capacitor, then XC will be minus J by omega C, is JXC. So XC is minus 1 by omega C. Is that all right? XC is always negative. So it is inversely proportional to frequency. It will be a rectangular hyperbola varying like this. So this is XC. If I put, this is tending to infinity. If I put a series combination of L and C, series combination of L and C, then what will be the net effect? It is XL plus XC, which is minus 1 by omega C. So this magnitude minus this magnitude, that will be the net result. So initially this is 0, this is minus infinity, so it will, the net value I will show by a dotted line, will go like this, and when this magnitude is equal to this, it will be 0. So the net value will pass through the origin at this point when omega L is equal to 1 by omega C. And then finally this is tending to 0, but this is increasing, so it will be asymptotically catching up with this. Okay. So this will be XL plus XC characteristics, total X. Is that all right? If I take a series combination, the reactance varies like this. What about the admittance? Let us see the admittance of this. It will be 1 over this quantity, okay, one by j omega L minus j by omega C. So how much is it? If I multiply by omega C divided by omega square LC minus 1, and j can be taken out, so minus j by omega C by omega square LC minus 1. Okay. If you take small value of omega, where will it tend to? Small value of omega, this is minus will go, this will tend to infinity, this will tend to infinity.
Because omega is there, so omega will get cancelled and omega when goes to 0.
Omega is tending to 0.
So
It will,
that omega will be cancelled, so one omega will be there in the denominator.
1 omega will be in the numerator.
So it will be going. Denominator will be 1 omega.
What will be the admittance function like? What will be the admittance function like when omega tends to 0, that is yj omega, omega tending to 0, infinity, omega tends to 0 means this is negligible, so this will be 1, and omega tending to 0, this will be tending to 0, so it will be 0. And plus or minus, will it be plus or minus? Plus j, a small quantity, plus j epsilon. Okay, so it will be starting from here, and as omega gradually increases, it will be having a slope very close to omega c. Neglect this compared to 1, so it will have a slope pretty close to omega c, I mean slope of c, it will be varying like omega c, and at omega tending to LC, omega square tending to 1 by LC, a little less than that, this will be a little less than 1, okay, say 0.99, omega L square LC is 0.99. What happens to that? This will be tending to 0 from the left hand side, that is say minus 0.001. So this will tend to, and what about this? This is minus j omega into c. So minus j omega into c divided by a very small quantity, negative say 0.001. When I am approaching this frequency 1 by LC under root from the lower side, that means this quantity is less than 1 in magnitude, say 0.9 or 0.99, then this is a negative very small quantity, so this will be tending to plus infinity, is not, it is a large quantity. So at that frequency it will tend to a very large quantity. When I just cross over that frequency 1 by root LC, what happens to this magnitude? This becomes suddenly plus, and overall quantity becomes minus infinity. So it will start from minus infinity, and then when this quantity gradually increases from 1.001 to 2, 3, 4, 5, so this will be gaining higher and higher values, so overall quantity will be reducing in magnitude, and at a very large value of omega this will tend to 0. So it will tend to 0 like this. Okay. You can have one or two more combinations of this, all right, a series parallel combination. You will find, for example, if we take a combination of one inductance, one capacitance in parallel, and then a series LC combination. Pardon? 1F. Thank you. So if you take such a combination, this will be the nature of function. If you put s equal to j omega, if you put s equal to j omega and then take out only the j, you will get x. If you sketch x, if you sketch the x against omega, you will get at those poles the function will try to blow up to infinity. Okay, it will be like this. It will be going up to infinity, and when you just cross over that pole, it will start from negative infinity. So this will be the nature of variation. In both the cases, I have taken a very simple order function. This can be proved for any other function. The slope is always positive, whether it is y or z. The slope is always positive. There is nothing like going down like this. The function is always increasing from a low value to high value. If it is a minus in the minus region, negative region, then from a very high negative value it is gradually going to less negative value. That means it is always increasing, whether it is y or z. Okay. All right. So one conclusion we can draw: the admittance, the reactance or admittance versus omega characteristic, if we study, the slope is always positive. Poles and zeros are appearing alternately. So henceforth we shall be indicating on the x-axis, which is the frequency axis, when we are making this x omega plot, these poles, it was starting from a 0 value, it was a pole here, then again, see, if it is only for xl, then again a pole. If you take the overall function for this was a pole, this was a 0, this is a pole. So poles and zeros will be coming alternately on the omega axis. Say if it is starting from 0, then a pole, a 0, a pole, and so on, then at infinity this will be a pole, then a 0, then this is infinity. Okay. This can be one configuration. If I am given the configuration for x, can you sketch the variation of x? It will start from a 0 and go to infinity with a positive slope. So what can be the variation? Can it go this way? It cannot. It has to go this way. So this is for x or y, either of them. Then from a pole, it has to go through 0 and approach again infinity. From minus infinity, it can go to plus infinity, passing through a 0. It cannot go this way. because then it will ensure a negative slope, and we have seen the slope has to be positive. Similarly, from this infinity to 0, it will asymptotically approach 0. This can be the possible x omega characteristics for a given set of pole 0 configuration. Is that all right? Let us take a function Zs equal to s into s squared plus 9 by s squared plus 4 into s squared plus 16. What will be the pole 0 configuration for x, and how will the impedance vary? Sketch it. Free s is in the numerator, so this one will be a 0, then 2 is a pole, then 3 is a 0, 4 is a pole, and then infinity has to be a 0 because last one was a pole. So from 0 on the poles we draw dotted vertical lines, and then it is very simple. It will go to infinity like this. From infinity it will go through 0 to this, then from infinity it will go to 0 asymptotically. See, this will be, so this will be the impedance characteristics of this function. Now my question is it possible to have a function like this, s squared plus 4 by s squared plus 9 into s squared plus 16? Now you see 0, 0, then pole, then pole. So first 0, 2, 3, 4 is not, the corresponding roots are 2, 3, 4. Can you have 0, 0, pole, pole? 0, 0, pole and pole. They should come alternately. Alright. So you cannot have this as a LC network function. Now suppose you are given a function Zs equal to 10 into s into s squared plus 9 by s squared plus 4 into s squared plus 16. Okay. Now how many informations are given to you? One is this frequency 9, the other one is, that is 3, 2, 4, 3 and one constant. So informations given are 4. So I can realize this network with minimum number of elements 4. Alright, this function can be realized by at least 4 elements. If I have a network of say 1 Henry and 2 Henries, this is not a canonic form. A canonic form means which requires minimum number of elements to represent a function. How much is this? Total is s plus 2s, 3s. So 3s I can realize by a simple 3 Henry inductor. Why should I have 2 inductances? So this is not a canonic form, this is a canonic form for that function 3s. If I am given Zs is equal to 3s, realize it, I will go for this. This is a canonic form. Canonic form means minimum number of elements required to realize that network function. So how many minimum number of elements will be required here? The informations that you are giving will be 4. So if you are given 4 informations, 4 minimum number of informations, then I can have only 4 minimum number of elements. Alright. So, this will be a network, a canonic network with 4 minimum number of elements. Now, if I make partial fractions, what will be the form? K1s by s squared plus 4 plus K2s by s squared plus 16. Can I have anything like K3s plus K4? Let us keep a general form like this. Since the roots are all on the imaginary axis, poles and zeros are all on the imaginary axis, there is no scope for any resistive element. So, Zs with a K4 means a resistance, so that is ruled out. Okay. If I add this, what will be the numerator? S squared plus 4 into S squared plus 16 into K3s, highest order will be S to the power 5. S to the power 5 is not given here. So, this is also ruled out. Had I had a term like S square plus 25, then the numerator was S to the power 5 maximum power. So, then K3s would have been possible. But in this case, we are having a maximum degree of S to the power 3 in the numerator. So, here if I add up, it will be S to the power 5. So, this is not possible. So, K3s is also not possible. Now, let us find out K1s and K2s. What will be the residue K1 multiplied by S square plus 4, okay, and divide by S. So, this S will go, then make S square plus 4 equal to 0. So, it will be 10 into 5, S square plus 4 is 0, means 5 divided by 12. Is that all right? So, 50 by 12, so 25 by 6, 4.16. K2 similarly multiply by S square plus 6, divide by S, make S square plus 6 equal to 16 equal to 0. So, this will become minus 7, this will become minus 12. So, 10 into minus 7 by minus 12. So, that gives me 70 by 12, 35 by 6, 5.83, 5.83. Okay. So, I have got Zs equal to 4.16 S by S squared plus 4 plus 5.83 S by S squared plus 16. What is this combination? If in an impedance function you get something like Ks by S squared plus alpha, what does it mean? If I make S tending to very, very small value tending to 0, this will be absent. So, it will be Ks by alpha. Ks by alpha means K by alpha Henry. Alright. Similarly, if I make S tending to infinity, alpha will be knocked off. So, it will be Ks by S square, S will go. So, K by S, so 1 by K farads. So, here I will get 4.16 S by S squared plus 4 will give me an inductance of how much? When S tending to small value, 4.16 by 4. So, that is 1.04 Henry. Is that all right? That means at a low frequency capacitor blocks the current, the entire current flows through the inductance. So, it becomes an inductive circuit. At a very high value of frequency, capacitance is a bypass. So, the entire current flows through this, it becomes capacitive. So, it will be 4.16 by S. So, S will go. So, 1 by 4.16 farad. Is that all right? Similarly, 5.83 S by S squared plus 16. Could you please tell me the values? When S is small, it is 5.83 by 16 Henry, and this one will be 1 by 5.83 farads. Okay. So if I put these two in series, I get the total impedance function this plus this. Okay. So whenever you start realizing the function from ZS, that is, take the impedance function, break it up into forms like this: K1S by S squared plus alpha plus K2S by S squared plus beta, and so on, plus a free term K3S plus a term K4 by S. In the previous case, I forgot to include another term, K5 by S. Is there any possibility of K5 by S coming? Because S is in the numerator, not in the denominator. So in this case, that was also ruled out. But suppose in the general function S is in the denominator, it is possible, then you will have a function like K4 by S also. So you have to see all possible elements of this type, either an inductor, a capacitor, or LC combinations. If I can break it up in this form and realize each element of this partial fraction separately, put them together in a string, that is called Foster-1 synthesis. Foster-1 synthesis. Let us take another example. ZS equal to S squared plus 1 into S squared plus 3 divided by S into S squared plus 2 into S squared plus 4 and S squared plus 5. Okay. So numerator is S to the power 6, denominator is S to the power 5. So what will be the form like? K1S by S squared plus 2 plus K2S by S squared plus 4. Will there be any K3S term? Will there be any K4 by S term? K4 by S will be present because S is in the denominator. K3 into S will be present because here it is S squared S into S to the power 6. S to the power 6 is present here. So for this type of function, all the 4 elements will be present. We realize after getting the values of K1, K2, K3, K4, what will be the network like? A capacitor of value 1 by K4 farad, okay, an inductor of K3 Henry, and then terms like this K2S by S squared plus 4 will give me a tank circuit, a parallel LC combination. How much is this when S tends to 0? K2 by 4 Henry, is that all right? And when S tends to infinity, it will be 1 by K2 farads. Okay. Similarly, this one K1 by 2 and 1 by K1 farad. This will be the network. Is that okay? Any question? If I have ZS like this, all the possible terms are there. Can I have another inductance or another capacitance in series? that will not be a canonic form, because in series you cannot have more than one capacitor in the canonic form. Another capacitor could have been added together, I could have got an equivalent value. Another inductor could have been added, but these cannot be added. So each one of them will give rise to one pole. Corresponding to each pole, like a square plus 2, a square plus 4, you will have one LC parallel combination. Since they are distinctly different, so you will have distinctly different combinations. But series combination, there can be only one K3 and K4. I cannot have another K5 by S. Then I could have put them together, K4 by S and K5 by S together. Alright. So
zeros can be different. Zeros can be different in the network. But the poles are unique.
no, I didn't mean that. Whatever be the given network function in the canonic form, you can have one series element of inductance at the most, one capacitance at the most, and parallel combinations of LC. Okay, each one giving rise to one pole, and depending on the order of the numerator polynomial, how heavy it is compared to the denominator. If the denominator is 5, s to the power 5, numerator is s to the power 6, then if you divide, you will always get a free s term. That means there is a series inductance. If s is in the denominator, there is a series capacitance also. Alright. So either this will be absent, or this will be absent, or both may be absent, or both may be present. So what will be the number of elements of L and C? How much can be the difference? See, how many inductances are there? 1, 2, 3. How many capacitances are there? 1, 2, 3. Suppose this is not there. This is also going to give me another function ZS. This is one possibility. So how many inductances are there? 1, 2, 3. Capacitances 2. Difference is 3 minus 2, 1. I can have the inductance absent. Then how many capacitances are there? 3. How many inductances are there? 2. Can you have 2 inductances and 4 capacitances? 2 inductances and 4 capacitances?
No, sir, then pole will be increasing.
No, let us see. The structure can be always like this. I can always get for any ZS function a structure like this. Now, suppose 4 capacitances. 1 I can put here, 2 inductances. So one inductance I can put like this, another inductance I can put like this. Now 3 capacitances are already gone. Where can I put the 4th capacitance? Still it will be a canonic form. It is not possible. If I put a capacitance here, I could have added them together. I cannot put a capacitance here, then I could have added this together. So I cannot have more than 3 capacitances if there are 2 inductances. To get a canonic form, that will not be a unique function. If I put a capacitance here, I find the overall ZS, and that ZS I can realize. Suppose you find out, suppose this is 1 farad, this is 2 farads and so on, you find out ZS, and again from there if you try to realize, you will be able to get a function like this. That means I can realize the same network function that you are giving me by less number of elements. So that was not a canonic form. So the difference in the number of elements L and C cannot be more than 1. They can be equal. L can be greater than C or C can be greater than L, but then the difference can be only 1. Is that all right? This is Foster 1 synthesis. If instead of that we would have started with an admittance function, say the same function ZS is given, I can realize it in terms of admittances, then what happens? So I will just invert it. YS will be S into S square plus 2 into S square plus 4 divided by S square plus 1 into S square plus 3 into S square plus 5. Again I make parallel, I make partial fractions, so it will be A1S by S square plus 1 plus A2s by S square plus 3 plus A3s by S square plus 5. Okay. Will there be A4s and A5 by S? Since S is not in the denominator, this is ruled out. Since it is already S to the power 6 and numerator is S to the power 5, so if I put this, then it will be S to the power 7. So this is also ruled out. Okay. So I will get A1s by S square plus 1. Let us call these as Y1 plus Y2 plus Y3. Okay. So what will be Y1? Y1 is, say, 2s by S square plus 1. Suppose it is 2s by S square plus 1. What does this mean? If I make S tending to 0, it will be going to 2s. So when is the admittance becoming 2s? Admittance is CS. In case of admittances, CS is the admittance, so it is 2 farads. So it will be a 2 farad capacitance. At that time, at a very low frequency, inductance is 0. It is a series combination. You see, if Y1 is this, corresponding Z1 is how much? S square plus 1 by 2s. That means S by 2 plus 1 by 2s. So half Henry inductor and 2 farads capacitor will give me this impedance, whose admittance is this. So each admittance you just invert and then separate, you will get the corresponding LC values. Is that all right? So similarly you get another LC combination, Okay. Interestingly, these values will be different from the Foster realization, Foster 1 realization. But how many inductances were there? 1, 2, 3 and 3 capacitances. You go for this realization, you will get the same number of elements, type of elements will be of the same number. 3 inductances, 3 capacitances. So if we go from impedance, it is Foster 1. If we start from admittance function, this is Foster 2 realization. Okay, we will stop here now. We will continue with this in the next class. Okay, good morning. Last time we were discussing about Foster 2 realization. Of network functions. Suppose you are given Zs and you have obtained Ys. Ys is, say, S into S squared plus 4 divided by S squared plus 1 into S squared plus 16. Okay. Then I can write this as K1 by K1s by S squared plus 1 plus K2s by S squared plus 16. How many elements will be there? Can you guess how many elements will be there? How many informations are given to you? I could have had a constant here, 10 or so. So this is one information, 1, 2, 3, 4. So you can have only a 4 element synthesis. Now each of these factors will take away 2 elements. So 2 plus 2, 4 elements are already gone. Alright, so blindly you can write there is no other term K4s or K5 by S. Okay. So how much is K1 multiplied by S square plus 1 divided by S, make S square plus 1 equal to 0. So 10 into 3 by 15, so that is equal to 2. K2, so 10 into 12 by 15, make S square plus 16 equal to 0. So this will be 12 into 10 by 15. 8. So I can write this as 2s by s squared plus 1 plus 8s by s squared plus 16. Okay. So this is y1s plus y2s. So how much is y1s? What are the values of L and C? Corresponding z1s, y1s gives me z1s, which is just inversion of this, s squared plus 1 by 2s. So that is s by 2, half Henry, 1 by 2s, so 2 farads. Is that okay? Another combination, y2s, how much will be the element values of y2s? Invert it, s square by 8s, that is s by 8, 1 by 8 Henry, and 16 by 8s, so 2 by s, that will give me half a farad. Parallel combination of RL elements. Is that all right? 7 by 32, 16 into 2, 32. Oh, 7, not 17, sorry, not 17, thank you very much, it is 7. 7 by 16 ohms resistance and 7 by 32 Henry inductance. So if you are having in the impedance function the first factor as a 0, then it will be an RL network. That means admittance function of RC network and impedance function of RL networks are identical. Conversely, impedance of RC network and admittance of RL network are identical. Poles and zeros, thank you. Poles and zeros will be alternately coming. If in the impedance function it starts with a pole, it is an RC network. If it is in the if it starts with a 0, it will be an RL network. And then the method of partial fraction is identical. All right. The partial fractions that you have made for admittance of RC network will be similar to impedance of RL network. Is it not? So in the next class we will be taking up some tutorial exercise on synthesis by different techniques of different RL, RC and RC LC networks. Thank you.